Hello, hello everyone. Thank you so much for joining this workshop. This is the second week we're doing application developer bootcamp, and today we are going to talk about data modeling, designing efficient data models for your application. Okay, this is the second week, and the last week we had the introduction to NoSQL databases, introduction to Apache Cassandra. And next week, there will be the third and final week of the workshop where we will build an application with a NoSQL database backend, in particular Apache Cassandra. Okay, and I participated last week as well with Alex. My name is Artem Chebatko, and I work for DataStax. My interests include data modeling, data quality, data warehousing, data analytics. I work with a number of open source technologies. You can see some of them here, including Apache Cassandra, Apache Spark, Apache Tinkerpop. I also work with almost any type of database imaginable, starting from relational and NoSQL and data warehouses and so on. And I also authored Cassandra data modeling methodology, and we are going to talk about it today. And today with me, Aaron Ploitz. Aaron, could you say a couple of words?
Hey everyone. I hope you can all hear me okay. I think I'm coming through all right from what I can tell. But anyway, hi, yes, I'm Aaron Pletz. I'm a developer advocate with DataStax as well. Yeah, I'm a database engineer by trade. I've worked on a lot of large scale Cassandra deployments at a few different like Fortune 50 enterprises. I'm also an author, written a couple of books. Occasionally, I still do write an article or two on Cassandra or whatever else we happen to be using over here. So yeah, that's basically it about me. So yeah, happy to be here, and yeah, looking forward to taking everyone through some great material.
Yeah, thank you, Aaron. So today we're going to focus on a lot of hands-on, and you will not need to install anything. We will have GitHub repository with information on different labs and demos and homework. We will give you a link soon. And we will also use Git pods to run those labs. And that should be pretty easy as long as you have GitHub account. You should be able to log into Gitpod and use our labs. They are step by step. You will not need to copy paste anything if you don't want to. So you will be able to just run through different steps and execute commands and see how they work in real database, real NoSQL database. And to simplify things, for database, we're using Astra DB, which is built on Apache Cassandra. This is cloud database as a service in the cloud. So it's easy to start. You can get the 3-node cluster with just a simple clicks of a few buttons there, and you will be able to access it using SQL clients and so on. So today, our agenda includes, we're going to still review some data storage content that we talked about last time. We will talk about key definition. Something new will be SQL data types. We'll talk in more detail about them, data modeling, and optimization techniques. So we do have a lot of content, and probably we will not be able to cover everything, but for sure we should be able to cover the first four, and we will focus most attention on hands-on, so you can get some skills of actually using the database and running those commands. And the first topic, Aaron is gonna
All
talk
right, so
about
let's see
data storage.
how our shift in screen sharing works out here, huh? I think we're okay so far. All right. So yeah, as Artem mentioned, I'm going to take us through this first section here on talking about data storage, as well as and a part of that is distribution and organization. So let's see here. Yeah. I have to say, Riggs, I really like. Oh yeah, by the way, Riggs is on is like the third missing head, but I really like how our bubbles kind of line up with the fancy new branding graphics. That's pretty cool, actually. All right, I digress. Okay, so a little bit about data distribution, a little bit about how Cassandra works, and the architecture behind it. Essentially when we're talking about Cassandra, we're talking about a cluster or many nodes which work together, as I'm sure many of you know. And each of these nodes, contains like a subset of the data. No one node contains every row, at least not in a large cluster. And they all talk to each other, they pass around what we call gossip that lets each node kind of know the status of the other nodes. And this is really, really important because it's what kind of leads to Cassandra really having no single point of failure, in that any node can handle a read or write operation. And it's also very, very easy to scale it in that sense for both reads and writes. And really, when it comes down to it, is that if there's like a hardware failure or an instance failure, something, and you happen to lose a node, the application doesn't skip a beat for the most part. It can find another node to talk to. Like I said, any node can really be a coordinator and handle a database operation. So I know there are a lot of preconceived notions out there about NoSQL and what people think of when they hear NoSQL, but Cassandra is actually a partitioned row store, and it stores data organized in tables, just like many other databases, which I'm sure folks are familiar with. Now, when it comes to that table structure, it's important to keep in mind, how those tables are keyed, because that really determines two things. It determines where in the cluster those rows are stored, and B, the order in which that data is going to come back when you query those partitions. So here, we have our sensors by network table, kind of thinking about a, like an IoT type of a temperature sensor network. So we have we have two sensors out in the forest on that network, and there are two sensors underneath. Simple enough. And if you want to query all sensors for a network, that's really easy to do. So the cool thing is that those rows for forest are stored together on the same node. So if I were to go and look at how the data in that table gets distributed across, around the cluster, I can see that both of my rows for the forest, if you can, you can't really see my mouse, can? Oh, you kind of can. Okay. You can see it's up here on this topmost node. You can see that the two forest sensors are stored together. Likewise, the sea and the car sensors are stored together as well. And we'll get into a little more detail on how the the partition key it gets like organized onto a certain node, which we can talk about right now, actually, because if you think about it, the way that data distribution in Cassandra and Astra DB as well works is that each node is responsible for like a range of tokens or token numbers. And the idea is that when you run a hash on that partition key, it comes back with a number which tells Cassandra which node that data row belongs on, or that partition belongs on. So in this case, as you can see, we're going to take that partition key of forest and we're going to run a hashing function on it. And we're going to come back with a token number of 59. Really, the numbers are much bigger. We're just kind of showing 0 through 99 just to kind of keep things simple here. But the actual range of values is like plus or minus 2 to the 64th power. So it's actually quite a large range of unique tokens that are possible with Cassandra. So anyway, in this case, if you look, it's the purple node on the bottom is the one that's responsible for the range of 50 to 66. So that's where the token of forest for 59 would kind of fall into play there. Now, also with Cassandra, we have this idea of replicating data, because if a node goes down, we want the cluster to still be able to move along and still process operations. So a common way to achieve that is by setting a replication factor, and the most common replication factor is 3, and that means that there are 3 replicas of each row of data out there. So if the purple node is responsible for, oh, bless you, Regs, is responsible for tokens 50 through 66, well, that means that their primary token range is going to be on that purple node. But there's also a neighboring node calculation that comes into play in terms of figuring out where the secondary and tertiary token ranges are as well. So in this case, the orange node and the black node are also going to be responsible for storing the data related to that forest partition. And in this way, data gets like spread and distributed across the cluster. All right. Now let's move on to a little bit about data organization. I talked a little bit about how Cassandra is a partition row store, and about how you're storing data in tables, something a lot of us are familiar with from other databases as well. But Cassandra has all of these structures which kind of help keep things organized. So the topmost logical organization bit is known as a key space. And essentially a key space is really just a way to keep tables organized. So key spaces contain tables. Tables, of course, are where we have our columns and where we have our keys, and then ultimately our rows as well. Now, a special part of the key or primary key in Cassandra is a part that's known as the partition key, which we've talked a little bit about so far. But really, that partition key is the piece of the primary key that tells Cassandra which node that particular row is going to be on. And in this way, you can see how a table can actually be distributed across multiple machine instances. Now, if we were going to create a key space, now, of course, for those of you who have used Astra, you know that creating a key space is a different operation. But it's easier, actually. But for Cassandra, creating a key space, it's pretty simple. It's just with this syntax. So if we were going to create a key space to store tables relating to, again, temperature sensor data, we could create that key space called sensor data. And we're going to use a replication strategy of network topology strategy. And the reason network topology strategy is important is because that's the one that allows us to specify multiple data centers. So if it's important for our application to serve data in multiple regions, like in this case, we're designating 3 replicas to US West 1 and then 5 out to EU Central 1. Now, again, typically you'd probably want to do a replication factor of 3 in both. This example is just showing 5 as a way to illustrate that replication factor can be set differently depending on which data center you're working with. Now, if we were going to create a table, simply put, you'd either be using a key space, or you could designate that key space name first, but it'd be a create table, and then your sensor data, sensors by network, and then inside of it you would specify each of the columns along with the column's data type, as well as the primary key definition. Now, in this case, for our primary key definition, we have 2 columns that we're designating as keys. Now, that first one is our partition key, and you can see it has an extra set of parens around it, just so that you could have a composite partition key if you really wanted to. Or not in this case, but that's why those parens are there. And the second key is what's known as the clustering key. Clustering keys are important because they actually determine how that data gets stored on disk and the order that it's in, which is also the same order that it's read back off of when there's a read operation. So that clustering key is actually important in determining, again, kind of the sort direction or sort order of the data that's returned, at least for that partition. Oh, I think I jumped back on accident. All right. Well, hey, I think we're at our first lab, or our first hands-on exercise here. So for this one, we're essentially going to go out and create our Astra database instance, as well as create our token and hopefully save that off somewhere. So that's going to be our plan.
Yeah, in the chat you should see the link for the GitHub.
Yep. Yep. So if I go to the GitHub here, and I'm looking at the README, our first hands-on is this section number 4 right here, which is this create your Astra DB instance. And it has a button here that I'm pretty sure takes you right to Astra. All right. So I already have a Astra account, so I'm actually going to go to the bottom here and say sign in instead of sign up. And we do offer single sign-on for those of you who haven't used it before. So you can use either like your GitHub or just your regular Google account to activate that single sign-on. So I always use my my Google account. So I'll go ahead and sign on with that. All right. Excuse me, it's taking a second to load here. Actually, you know what? Why don't I
Oh, nice.
Oh, okay.
Can you hear us now? I
Yeah,
think so.
I
Yes.
I hear us. I think we're all right.
Oh, we are very sorry. How long we
Yeah, how
miss it?
long were we out for? The silent screams. That's pretty funny. Did anyone hear anything about you know, how to build a new database? Should I go through that again? Logging into Astra was the last thing. Roger that. Okay, okay. You know what? We'll just go ahead and we'll walk through this one more time. So I'll do this, hit this create database button right here in the middle. And this time I'm going to say workshops 3. Although, as Artem noted, let's make sure that you know, that you're using workshops without a number on the end. All right, so I'm going to use that sensor data key space name, which again is right here in the README. I'm going to make sure I'm selecting Google Cloud, and I'm in North America. And the one free region I have here that doesn't have a lock symbol is this Moncks Corner, South Carolina. So that's what I'm going to select. And yes, I'm on the free plan. So let's do a create database. Okay. Oh, you know what? That time it didn't pop up with a new token. That's interesting. Well, again, I'll say this, that the token, this is what I was saying when we realized we you know, didn't have sound. That the token that gets created by default does not have enough permissions for what we need to do today. So we're actually going to create one right now. So I'm going to go to, oh, let's see here. I think I just need to go back to databases. And yeah, here we go. So if you're back at your main database screen, you can see that I have my workshops database here, and it is active. I can click these 3 dots way over here on the left, and I'll get a small menu that pops up. And this middle option here is generate a token. So I will go ahead and click that. Now I want my role, and of course you open this up and you get just a ton of different roles that you could choose from. I'm going to pick database administrator because we are going to be creating some tables today, as well as some types, I think. So it will help to have that permission. So I'll say database administrator, and I'll go ahead and say generate token. All right, so now you notice I have my token details right here. I could copy and paste these individually with these little icons here, but I'm just going to say download token details. I'll, as you can see, it did actually, you know, show up down here as a CSV file. So I'm going to go ahead and hang on to that for later because we will need those.
To the other labs, you will use that token to be able to connect to Astra DB, to your database, using a client, not going through the website, but using a separate client.
That's right. That's right. Okay, well, hey, Artem, I think that brings us back to you for talking a little bit more in detail about keys.
Yes. So, and we already talked about keys, but we'll talk about them again because this is one of the most important aspects of designing schema for a table. So if you understand how to design primary key, partition key, clustering key, you will be halfway done with data modeling essentially. And then the data modeling itself can be a process that takes many more steps than just designing the key. So primary key, why primary key is so important? Because it defines how data will be stored. And we said that primary key consists of partition key, and partition key is always required. So it's mandatory key that you have to specify. And it can optionally contain, the primary key can optionally contain definition for clustering key. So clustering key is optional. Partition key, we said that it used to distribute data over nodes in the cluster. The partition key the values will be hashed, converted to tokens, and then each node knows which tokens they handle. So that's primarily purpose is to distribute. And of course, we want to distribute uniformly. We don't want to have too small partitions, too large partitions. We don't want to have nodes where there are so many partitions and some other nodes with just one or a few partitions, right? So we want to kind of uniform distribution across nodes. So designing partition key is important. And the clustering key, which is optional, is going to define data uniqueness and ordering within the partition. What does it mean? So within the partition, you may have multiple rows, and they all have the same partition key. But you want to make sure that you can refer to those rows one by one to uniquely identify any of those rows. So you will need additional key, which is called clustering key. And then besides that, automatically, Cassandra is going to order those rows within the partition based on the clustering key. So default ordering will be ascending, but it can be changed to descending. So here is the definition of the temperatures by sensor table. We have partition key here, which is composite partition key consisting of sensor and date, 2 columns. And timestamp is a clustering key. And we do change the default ordering of timestamp to descending, which means that the latest measurements from this particular sensor on a particular date will be at the top of the partition. And we can actually retrieve that. For example, we can retrieve from that partition limit 1, and we will get the latest measurement. Limit 3, we will get the latest 3 measurements. So that's pretty useful. Okay. Besides that, very important to understand is that primary key defines how data is retrieved. So you can only retrieve data based on how you define your partition key. So when you partition and clustering key. So when you define in primary key, you're thinking about how you're going to use a table, how you're going to query that table. So for this example that we have, sensor date as a partition key, timestamp as a clustering key, we have the following patterns. Okay, we for example, we cannot select from this table where sensor equals something, because we have to specify the complete partition key to retrieve data from this table. So we cannot retrieve based on just sensor ID, based on partial partition key. We cannot do inequality on any partition key columns. So we cannot say greater than, we cannot say where sensor equals something and date is greater than something. We cannot do that. So for partition key, it's only equality. So when you design in your tables and primary key, before you even design that, you need to know how you're going to use it, how you're going to query, how you're going to retrieve that data. So you need to specifically have that equality, inequality, and then based on that, you will design the primary key. And we will talk in more detail about that. So what is possible for this particular definition to retrieve data? You can retrieve based on sensor equals something and date equals something. You can also add timestamp into the picture. So and timestamp is equal something or it's greater than something. So if you say equal something, then you basically have all values, defined values for all primary key columns, and that means you're going to retrieve one row. But if you say timestamp is greater than something, you can potentially retrieve subset of rows, right? So storing and retrieving. And another important part about primary key is that once you define it, you create your table, you load data into that table, it's not possible to change it because the data itself is organized based on that key definition. It's partitioned across nodes, it's sorted in the partitions, so it's difficult to change it. And essentially, if you decide that you need to change it, that, okay, this table has either, for example, the partitioning is not uniform enough, or maybe it doesn't support your queries that you want to be able to execute. So it's basically queryability of a table is also affected by primary key. Then you will have to create a new table with primary key that you want, and then you'll have to copy the data from the original table to the new table and drop the original table. So it can be an expensive operation. You can think about it if you already have your data in the database. If you have terabytes of data loaded, then transferring that data may take a little bit of time. So two important concepts that I want you to understand very well today. So based on the partition key and clustering key, based on the essentially if the clustering key is defined or not, you can designate tables, or you can define them, or you can call them single tables with single partitions and tables with single row partition, tables with multi-row partitions. So in this example, we have tables with single row partitions. And how do we create them? These are tables that do not have clustering key. They only have partition key defined as part of the primary key. So in the first one, we simply store users, and we identify them by partition and identify them by email. So in this case, I can move the parentheses around, one of the parentheses around the email, so I can just have table definition that looks just like relational tables. Indeed, it will be just the same idea as relational table. So there will be not much difference. The only difference is that it's distributed in the cluster, right? On the storage level. But logically, it's just a table with email as primary key and partition key. So imagine you inserting a user with email A. You will insert that user into one partition, right? Because that partition is defined, that partition A. You insert in a user with a different email B, you will insert that user into a different partition B. Now, if you decide to insert another third user with still email A, you will basically similar to like you overwriting the first user that you already inserted with email A. So partitions here can only store one row, one single row. So this is important, and this is something that you're going to create this table in the exercise or in the lab that follows this section. And the other type of tables are tables with multi-row partitions, and most of the time you will have these types of tables. You will have clustering key there. You will have multiple rows in a partition. Why is that? Because that's how you're going to query your data. Most likely, you will have some tables where you retrieve users by email, but maybe if you retrieve users at a particular location in a particular city, then you will need city to be partition key, and you will need email to be clustering column or clustering key. So here's of ratings that user leaves, ratings by user, table name, and the user and the partition key. But within that partition, the email will be partition key. In that partition, there will be multiple rows. Each one is going to have unique title and year, which is identifier for the movie, and there will be rating there. So we'll have multiple movies nested in that partition, that will have different ratings. So in this case, the email is a simple partition key. The clustering key is composite clustering key, and we have compound primary key consisting of two keys, right? In the second table, ratings by movie, we have and year as a partition key. So each movie will have a separate partition, but then there will be emails of the users who left that rating and the value of the rating. So within partition, you will have multiple rows recording those ratings that different users left for that movie. So here we have composite partition key, and we have simple clustering key and compound primary key. Okay, so for the second lab, you will actually create those tables and see how they work, see what types of keys you will be able to execute over them, over those tables. Okay.
And you'll also need your token for this, so make sure you have it handy.
Yes. And and I don't have the token for that database that you created, so I will create a token one more time so you can see how it's done. So this is the section 5 of our README file, and there are two links here. Okay, so this is the first link. Open a new tab, and what happens here is you will need to log into Gitpod. In my case, I'm already signed in. For that, you can use your GitHub account. If you don't have a GitHub account, you may have to create it really quickly. And then you will wait a little bit of time. Okay, it's going to load. The project is going to load, and you will see the instructions. Okay, so things happening, and now you see the instructions on the left and terminal on the right. Okay, and so you can use the either local deployment of Apache Cassandra. For that part, basically what you will do, there will be Cassandra installed for you, and you will be able to use it. But once you close this window, once you close this workspace, everything will be gone. So instead, we will use Astra DB, connect to it, you will see, and then for that, we will need the token. Right? So I will go back to Astra DB website. Okay. Go to databases again. So if you did not create a token, this is a time to do that. And I'm going to use the workshops database. Okay, generate a token. Don't share your token with anyone else, and you will. It's a secret information. You will be able to access the database. So I will choose database administrator role. Generate token, and you can either download it with. I will copy it and leave it somewhere in a text file separately. So you don't need client ID secret and client secret at this time. These are like user and password. You will just need token in this case. So I copied it, and let me save it. Okay. So the next step, I'm gonna go back to my Gitpod, click Start with Astra DB, and the information here, you can read more about tables, single row partitions, multi-row partitions, but we already talked about it essentially. So there is syntax for the create table statement, and we will talk about some of those things like data types again. But here in step 3, you are able to start executing commands in the terminal. So I'm going to click Astra Setup. What it's going to do, it's going to install the Astra CLI. So it's a client that is able to connect to Astra database in the cloud. Okay, and that database is workshop database that we created and that you created token for. So I need to copy paste this token. The first time I copy paste something, I will need to allow it. Okay, and now I am connected to my database in the cloud. So I can list my databases there. There are two of them. I can create, and I should create, we are going to use for this lab, we're going to use different key space, the same database, but different key space. Database can have multiple key spaces. Done, we created key space. We can list all key spaces in our workshops database. Okay, you can see there are two of them now. The sensor data that we created before, and we're going to use it again later today. And this new key space where we will experiment with tables with single row partitions. Now, the last command here is to clear this terminal screen and start CQL-sh, CQL shell. Okay, so now we will be able to execute CQL commands. And at this point, you should be able to, so we just did this simple setup. At this point, you should be able to recognize the stable users with email. I'm going to show you this first step and you can proceed on your own. So I'm going to create these stable users, insert some data, and then the only query that this table supports right now is selecting from users where email is something. Okay, that's the only efficient query. Okay, so, and I can retrieve one specific user. Even so, I inserted two different users, Joe and Jen. I can see them, but this query that selects everything is not an efficient query. We don't run it in production because it will have to reach all the nodes potentially and retrieve data from all the nodes to the client. So this will be expensive query if you have a large table, right? So the only query that it supports is efficient retrieval by email. And at this point, I would like you to, if you have any questions with setup, or you already was able to do the same thing that I'm showing you, but at this point, I want you to try to work with other tables.
Yeah, if anyone has any issues, feel free to drop a note in the chat.
Okay. So movies, another table that you've seen in the slides, but there are also some exercises for you. Can you create a table that stores genre information, adventure and what it is, description? So you can try creating this table in the terminal. And you should use tab for auto completion.
Just a quick check in the pulse of the room. If anyone's like I said having trouble, feel free to mention in the chat. But also, if you're actually going along in the exercises and things are working out well, feel free to add a thumbs up or something as well.
Yes. Or maybe even just which step are you on would be helpful.
Right. Right. Okay. Well, hey, Michael, it's good to know that you're following along as best you can there.
And you can always do these exercises after the workshop because they will
That's
still
right.
be available.
Yep.
This environment is free. The Gitpod environment and those links are still will be there in GitHub.
Yeah, that is always a question that we get asked in almost every workshop without fail. But yes, the live video we're doing now will be a video that is around forever that you'll be able to replay later, kind of at your leisure. So no pressure. All right, Artem, I think we could probably move on. Okay.
Sure. So the second exercise, or the second part of this lab, is for tables with multi-row partitions. Okay. And exactly the same story here. You will start the Git pod and you will be able to execute commands and see how those tables work. So I will do a few in the beginning for you.
Yeah, just a reminder, this is actually, I'm pretty sure this is a new Gitpod environment, so you'll need to re-enter your token again with Astra setup. Just a heads up.
Indeed, yes. Yep. Indeed. So you will need your token. Start with Astra DB. Skip the explanation this time. We will still set up the CLI so we're able to connect. I can skip some commands, but I will create new key space. And start CQLSH. So now this client is running in Gitpod and is connected to your database cluster running in the cloud, in particular in Google Cloud. That's where we created it. Okay, so we have table ratings by user. Let's create this table, insert several, 4 rows. But the question is how many partitions? And you can probably answer, we have 2. So since email is a partition key, we have 2 different emails. So we have 2 partitions. Each partition has 2 rows in it. So to retrieve 1 row in a from a multi-row partition, you will have to set the email, title, and year. So basically, all columns of the primary key. So when we say email equals Joe, title equals Alice in Wonderland, year 2010, then we get this 1 row retrieved from 1 partition. This is super efficient query. That's how you want your access patterns to be, right? So no matter how much data you may have millions, billions, trillions of rows in that table, but if you retrieve in 1 row using this access pattern, partition key, clustering key, this query is going to be super efficient. Now you can, if you only specify email, which is partition key, you will retrieve the whole partition. So all rows in that partition. In our case, we only have 2. This is also very efficient access pattern. The only time when it becomes less efficient is if you have very, very large partition. If you have billions of rows, or actually hundreds of thousands of rows in that partition, then you will have you will have a slowdown because one node will have to retrieve the data into memory and send it to the client. Right? So, but with 2 rows, with 10 rows, with 1,000 rows, this is extremely efficient pattern. So if you want to retrieve all the ratings that one specific user gave, we can use this query to do so. And of course, we can select everything. This is very inefficient access pattern. We should not be using it in production because it retrieves all the data from the table, which could be a huge amount of data. Okay. Similar idea for the next table, ratings by movie. So we can create a table, insert exactly the same ratings, but this time the same data is organized by title year as a partition key and email as a clustering key. So we can retrieve one row by again specifying all 3 columns in the primary key. And we can retrieve one partition and we will get 2 ratings. For this movie, we have a rating given by Jen and rating given by Joe. Okay. So this is a main difference between these 2 types of tables, right? So if you want to retrieve just one row, maybe you can use table with single row partition. You know that you will retrieve data multiple rows, then you need to define table to retrieve data for to be able to store multiple rows in the same partition. Okay, so let us know if you have any questions or if you are ready to proceed. We will give you a couple of minutes, then we'll continue. And while you're doing that, for those who either finished or just listen in, I'm going to talk about the so when you use multi-row partitions, this is when you basically have some entities related to some other entities, for example, or you have like one-to-many or many-to-many relationship between different objects, and you want to retrieve, for example, users who rated a movie, for example. So you have a relationship between those users and a movie, or you want to retrieve all accounts that you have in a bank, checking account, saving account, and so on. So you have multiple accounts belonging to one person. So if you want to retrieve all the account information at the same time, you want to nest that information into one partition for that particular user. Okay. Single row partitions, usually we query entities, objects by their key, by their unique identifier. Multi-row partitions is when you query relationships, how different objects that are related to one object. Okay, like attendees of a conference. For a given conference, I will list all the attendees, or I will nest all the presentations in that conference. Okay, so we finished these 2 exercises, 2 labs, and we can go back to we can go back to the slides, and let's talk about a few more things related to keys and related to partitions. Okay, so rules for good partitioning, and there are 3 of them. So something that you need to think about when you're creating tables, even the so when you're creating defining those keys, you usually think about how you're going to retrieve the data, what type of queries you will be able to execute, right? Whether you need to nest more rows in a partition, or will be fine with just one row in a partition. But also, so this is the first rule: store together what you retrieve together. Okay, so if you're going to have a query that says show temperature evolution over time for specific center on specific date, right, then you can specify, you can have your key defined like that. It will have the, sorry, okay, switch to it quickly. So sensor ID will be partition key, and timestamp will be clustering key. Okay, but why the first one is not gonna work that great? Because it's the temperature evolution, right? Temperature evolution over time. So this is a date, but you will have the multiple timestamps on that date. Maybe timestamp is the measurement is generated every second. So you'll have many timestamps on that date. So if you define like this, you will have to specify both sensor and timestamp to retrieve one row. But you need to get the evolution. You need to get multiple values, multiple rows. So you better nest those multiple rows in one partition. But this is not the best, not the final solution here. We will explain why. Why is because you also you want to avoid big partitions. So you don't want, so in this definition that seems to be fine, but the problem here is that if you're going to collect your data for months, for year, for multiple years, you will keep growing that partition. So it's not limited how many measurements will be inserted there. So you will keep growing, and over time, your partition may become too large. And too large, we're talking about 100K, 100,000 values in the partition, and 100 megabytes of worth of data in the partition. But in reality, you want those numbers to be lower, maybe divided by 10, if you want things to be very efficient. So the solution here is to introduce additional column into partition key. In this case, this is date column. So basically, on every single day, you will start a new partition for that sensor. So you will only collect measurements for that sensor on that date into that partition. Okay, and then next day you start a new partition. So that way you limit the growth of the partition to one day. And maybe one day is fine, depending on how often you take the measurements. If the sensor only takes one measurement per day, then it does make sense to split it by date. You may split it by year, for example. So instead of date, you will introduce year, and so on. So this is the second rule. We want to have big partition. The third rule and the final is that we don't want to have hot partitions. Hot partitions means that there will be too many requests coming, either read or write requests coming to those specific partitions, and we designate them as hot partitions. Why is it a problem? Because those partitions are handled by specific nodes, and there may be several replicas. So those nodes will become very busy because everybody is looking to access partitions stored on those nodes. One example of hot partition, the partition that could potentially be hot, is this definition. So syntactically and with respect to big partitions and with respect to storing things together, it's fine. But with respect to being a hot partition, it's not, because look at we partition based on date, and then sensor and timestamp is a clustering key. So if we partition based on date, then every day, from all the sensors, all the measurements will be going to one partition. Okay, will be going to one partition. So it definitely violates the rule of avoiding hot partitions, because on that specific day, there will be only a few replicas that handle this partition that will be getting requests. Next day, there will be potentially 3 other replicas that get in request for that date. So you're not distributing work uniformly among your cluster. So much better is this definition where date and sensor will be partition key. And you can, in this case, whether it's date or sensor, date, it doesn't matter. You can switch the ordering in the partition key. Not so much in clustering key. If you have 2 columns in clustering key, switching their order will also change how you can query your table and how the data will be ordered within the partition. So that's switching order within partition key is fine, but not within clustering key. Okay.
Oh, yeah, there was before we get into the homework, there was a question earlier from Raphael K about asking, can you have secondary keys for a table? Which I assume is like secondary indexes. And yes, Cassandra and Astra do offer secondary indexes. I mean, they aren't efficient, but my answer in the chat was that yeah, they're useful for smaller like corner cases. Think about it for it's a way to by convenience. It's not something you'd want to really run a lot of though. But yeah, Artem, I would love to hear your take on that as well. If you had something additional to add there.
Yeah. So I'm not. Most likely, this is about indexes. The other way to interpret secondary keys as like in the relational database, you can specify a candidate key
right.
by saying that's something unique. You cannot do that. No candidate key. So there is only one primary key. There is no uniqueness or other integrity constraints defined on other columns. But in terms of secondary indexes, they are there. They are available. They are for convenience, not exactly for performance.
Right.
And maybe that's one of the topics. If we have time, we cover that topic in good detail in the optimization section. So at the end, we will skip something. Maybe if we don't have much time left, we will skip other optimizations, but we will talk about secondary indexes because it's very important, I think.
Yep.
Okay. Do you have any other questions?
I think we're okay. Yeah, I think we can move on to the homework.
Yeah, for the homework, you can do it on your own if you want. This one is not going to be, we're not going to grade it. You will not submit it. But the second homework, you will be able to submit if you want to get a badge. But this first homework is a little bit more advanced. Even so, there are not many steps there to do. But this is something you can see on your own. And we will continue to the next topic. So Aaron, you're gonna talk about SQL data type.
Let me get my screen share ready. And then, all right. So, yep, as Artem mentioned, we're going to just cover, a real quick review on SQL data types. As you can see, there are a lot of them. You have kind of your your standard ones of like integer of like your numeric types like integers, as well as like your floats and doubles. There's also instead of fixed precision floating point types, we also have a variable precision decimal type as well, which is again what you should be using for something like where you absolutely care about an accurate value, like anything with currency. It's always a good idea to use that. A lot of times on Stack Overflow, I'll see questions about, hey, is there any difference between like varchar and text? And well, actually, no, there really isn't. They both come out to like a Java type of like a string. Time UUID and UUID, most languages I've seen just have a single UUID type. I know that's how it's handled in Java, and that whether you create a time-based UUID or a random type 4 UUID, like everyone's kind of used to, like a GUID, I think is what Microsoft calls it. But they're all stored in the same like UUID type. But Cassandra does kind of split those out to type 1 and type 4 UUIDs. So that's an important difference to call out as well. Let's see here. If I go on to the next slide here, you'll notice that Cassandra also has the collection types available. Again, Cassandra's written on Java, so it does a good job of exposing like a lot of the similar collection types which Java relies on, such as like sets and lists and maps. Again, depending on your language, those may map to different things. Like I think in Python, a map matches to like a dictionary, if I remember right. But additionally, inside of Cassandra, you can also create user-defined types as well. And this is really useful. And the example I was going to give was address, and it's funny that this is the slide that Artem had for it shows address. So a lot of times, when you have, customers for e-commerce, they may have multiple addresses. So you could have a list of type address, and that way your customer could have like a mailing address, a shipping address, a billing address, anything that might be a little bit different, or any reason that they might have multiple addresses. That would be a way that you could help track those as well. And of course, too, Cassandra also has tuple types. For those of you familiar with tuples, it's like a just an ordered, comma-separated list of values. Typically it's like 2 or 3, but yeah, you can also use tuple types as well, as well as your own custom types as well. Although that's a little trickier on the implementation side, so that's not something that we recommend people pursue if they're not not on the like advanced level. But yeah. All right, so now we have homework number 2 of working with types. Artem, were we going to spend a lot of time on this, or is this something that they can do later on, do you think?
Yeah, this is basically homework. We are not going to spend much time here. The only thing you need to know where to find it, it's in the same GitHub repo, the same README file. So for this second homework, if you complete it and submit via Google form, you will be able to get a verifiable badge that you participated
and
so that's completed this
section
workshop.
7 here. And I think the badge, oh, look at that. We even have a picture of the badge there, just so that you know what you can earn there. All right. Well, Artem, I think that goes back to you for data modeling.
Yes. So this is the main section probably of this presentation. It may include some little bit more advanced concepts, but hopefully, I mean, you don't need to understand everything, but hopefully you will get a few things from this section. So we'll talk about normalization versus denormalization. This by itself, we're going to just briefly touch it and why it's useful for Cassandra and for NoSQL databases. If you're familiar with normalization in relational databases. So normalization is defined in relational databases specifically to structure those tables in a relational database such that we avoid certain anomalies. And those are called in relational databases like update an anomaly, delete anomaly, and insert. So it's essentially what we want to make sure when we design in relational tables. We want to make sure that they do not duplicate data too much. And there are normal forms defined. They are based on functional dependencies within the table. The normalization is If you haven't touched it before, then you will find out that it's a lot of math there and specific algorithms to decompose those relations and all of that. So here's an example, simpler example here, that we have two tables, one employees, another one departments, and so employees has key or primary key, and this is relational tables, right? The ID is a key here, and it uniquely identifies each employer. There is a first name, last name, but then there is a department ID which references. So this is also a key. It's called foreign key in the relational database, and it's basically a reference to a key in another table. So this one and this one, they reference to this row, this key department ID in table departments. So this way, you know, hey, my mouse is too sensitive sometimes. So this way, you know that Edgar and Boyce, they both work or they belong to engineering department. But by looking at this key, you also know that second key, Alan Turing, belongs to math department. Okay, so this is how it works, and you can guess that this relationship is a one to many, or one to many, or many to one, depending which direction you read. So each department has many employees, or many employees can belong to one department. Okay, so this is basically one to many. In case of many to many, the key of employees will be, but we don't want to go into that. So this, if you know the normalization theory, you may recognize as a third normal form for this table employees. And if you want to find out which, for example, which department does Edgar code belong to, then you will have to do the join between these two tables. You will retrieve a row for based on, for example, ID of Edgar code, and then you will have to get the department ID and join it with this table departments, so that you can know that it's engineering department. So it involves a join, right, in relational databases. Cassandra doesn't have joins, and many NoSQL databases, many distributed databases don't have joins because they are very expensive. You have to get data from different tables, from different nodes in the cluster, and then somewhere you have to perform the join and only then return to the client. So most of the time there are distributed SQL engines as well, for example, Spark SQL that will allow you to do that, but that's not real time. That's not something that you're gonna return to the user in a few milliseconds. Sometimes those joins can be expensive and they can take seconds, sometimes minutes, sometimes hours, right? So that's not really OLTP database. So what happens with denormalization? It's the opposite process. You don't want to normalize to avoid duplicates. Instead, you actually duplicate data, so you avoid joins, and you nest the data into the tables. So if you want to retrieve now, in this table employees, we have we added department engineering right here to this table, and it's still in the previous, in the other table department. So in this case, we actually, if you look at this table, this is suddenly, this is no longer third normal form. This is, I think, second normal form table. The benefit of this table is that now, if I want to know which department does Edgar code belong to, I can retrieve it from one table. I don't need to do a join. Very efficient, right? Yep. The problem, what's the problem is that we are going to have those anomalies that referred in relational databases, where if we change the name of the departments, instead of engineering, we say computer engineering or something else, then we will have to suddenly update this value engineering, not just in these table departments, but in every row of the table employees, right? So that can be a little bit more expensive to do, and that can be that can involve human error. There is more likelihood of a human error forgetting to update something. But this is how NoSQL databases work. And again, another important distinction between relational and NoSQL databases, why they work like that. Why they work? It's, of course, it's efficiency, right? You want to avoid join and you want to retrieve data very fast. Even so, you have to have some trade-offs. So relational versus NoSQL schema. So one important thing to understand is relational database is an integration database. So what it means is that you have an enterprise with different departments, different functions, and there will be one database, usually one database that stores data for different functions. Okay, so there will be delivery department, there will be ordering department, there will be suppliers, all of that in one database, right? And we see that in relational databases, we see that in data warehouses. So that data will define the schema, okay, in the relational database. And then you will build multiple applications over that schema. You will do joins, you will do what's necessary. So your applications do not affect schema. You simply build them based on the schema. Somebody else usually defines that, database designer, administrator, define that schema. It's normalized. It stores everything very nicely based on mathematical normalization theory and all of that. But the problem, the applications will have to join. There will be different applications for different functions, different application for ordering, different application for delivering, different application for suppliers. So, but this is what is integration database is. And if you have a large enterprise with a lot of data and it's global, then the relational database is not going to be able to deliver this for you. That's why we have NoSQL databases that are designed very differently. The schema for these databases is defined both on data and applications. So it's an application database. NoSQL database, each instance, each key space you create is probably for a different application. And you define tables there with respect to both needing to store certain data, but also be able to retrieve that data based on queries that are needed for that application. So the schema is designed based on those things. So you can see the distinction. Only one app here versus multiple apps that access this schema. But here you focus on one app, and different functions will have different databases, different key spaces potentially. Okay, so that's a big distinction. Now going to the data modeling methodology, right? So schema design is one thing, is when you define the table, create table. These are the columns, these are the data types, these are the primary key, partition key, clustering keys for that table. But data modeling is much more than that. And we will, of course, not be able to touch that. But just for your understanding, you start your data modeling by looking at data requirements. What do you need to store, right? Identifying how that data, what types of objects, entities, and how they related. So you identify how that data will be used in application. So those are your access patterns. Those may be inserts, maybe complex transactions, maybe certainly queries, maybe some other things like batches and all of that. So once you have that, so this is data and application together. At that point, you will be able to organize and structure your data and design the database schema. So database schema is almost the last step. The very last step will be schema optimization, thinking about, well, can I replace this table with just an index on a different table? Can I replace this with materialized view? What happens if I have concurrent access to this? Should I use lightweight transactions? Do I need to split partition because it's potentially going to be too large? much. So you analyze and you optimize. The optimization is the next topic, and we will probably be able to touch at least indexes, I hope. So all this will affect completeness of your data model. So you store everything that you need, consistency, accuracy, and also data access. Will you be able to execute certain queries or not? That will be defined by data modeling that you do. Will your queries be efficient? Will they scale, right? Once you load, now you testing with 100 rows, but once you load billion rows, will you still get the same performance? Assuming, of course, you increase the number of nodes in the cluster. But will that data be nicely distributed across those nodes, and you only get the very specific partition to answer that query? So there are 4 data modeling principles. The first one is know your data. And by that, of course, you will, okay, I will have users, I will have orders. What people frequently overlook is keys and cardinality constraints, because they will be very important when you design your primary keys for the tables. So what uniquely identifies entity, and what is the relation, what cardinality relationship between 2 different entity types, right? How many times user can rate the same movie? Is it once, or is it 10, or is it multiple times, right? So all of that, if it's once, then the primary key of a table that captures that relationship will be different than if it's multiple times. And then you have to say, if it's multiple times, then you have to add timestamp of that rating and make it part of your key. So those are important things. Know your queries. Like we said, the queries will drive the schema design, because you need to tables to support specific queries. Nest data. Nest data is universal concept among SQL databases. And sometimes we call it denormalization. Sometimes other databases call them aggregation. Sometimes people say what you need to retrieve together, you store together. But essentially, we need to nest rows in the same partition to be able to retrieve those rows efficiently, right? And how do we nest data in Cassandra is using those tables with multi-row partitions, using clustering columns. That's one nesting mechanism. Another nesting mechanism would be the set and list and map, the data types that we've seen just recently. But those data types are for very small data sets. So you don't want to have more than 100 values in a list or set. While with clustering columns, you can nest thousands of rows into the same partition. And the last one, very simple. It's better to duplicate data than to try to do a join. You can still do an application join if you wish. So you can retrieve something from one table, get the ID and retrieve from the next table in your application. But that's not the most efficient access pattern. The most efficient access pattern is you want to touch one partition in one query. So you need to design those partitions, those tables, to be able to do that. So to formalize this whole process, right, we need to understand the data, and this is done with conceptual data model. I will show you an example, entity relation diagram. To identify access patterns, we can formalize, so we can have a document called application workflow model, where you will see the different queries or potentially complex updates, maybe deletes, and so on. And you will see how they depend, because what is the order of execution based on dependencies between different tasks in your application. So this is what you do before even you start creating tables. And then once you have those 2 things, you understand the data, you understand how it will be used, you can map that into first schema, applying the query first approach, and you get the logical data model, and you will see Chebotko diagram as a way to represent it. And then once you do that, the final step step is when you optimize and you get the physical data model that now can be instantiated in CQL, Cassandra Query Language, and you can now create it in the database. So let's look at those steps. The first two: understand data, identify access patterns, conceptual data model, application workflow model, how they work. So this example of conceptual data model that we want to create, we want to be able to support for our sensor data, and we will actually create in the next lab. You will create the schema for this new database. But now we're designing this schema, how we are designing it. All right. So we conceptually we have networks that have sensors, and each network can have many sensors. Each sensor belongs to exactly one network. Sensor records many temperature, it takes many temperature measurements, and each measurement belongs to is recorded by exactly one sensor. Now there are attributes that describe network, for example, name, description, region, number of sensors, and name is underlined here as a key attribute. So it uniquely identifies the network. For sensor, it's ID, but also there is a location with latitude and longitude. So it's basically composite attribute, and the sensor can have multiple characteristics, so multi-value attribute. And the measurement, temperature measurement, is identified by both timestamp, so that's why it's not underlined by solid line, so it's a partial key, and ID of the sensor. So this is called in entity relationship model. This is called weak entity type, and sensor is a strong entity type, because weak entity type doesn't have enough attributes to form a key. So this is very precise definition of my data. Of course, I can write it down, just a bunch of text, how I understand the data, but instead, if I have this, I cannot make a mistake. I know how to read this. I cannot make a mistake. Everything here has enough information for me to do my data modeling tasks. The second important model is application workflow diagram. This one is super simple, because simply you think about, so what my application will do. Well, first, once you log in, for example, or you will show all sensor networks. To do that, you will have to access database and find information about all networks, and you want to order by names. So this is the first query. So this is the first access pattern. After that, the user in your application may decide to either display a heat map for a network, or maybe display all sensors in a network. The second one is more complex query. Let's look at the third one. For simplicity, find information about all sensors in a specified network. So, and then the next task, and the next task. So we have very simple workflow for this presentation, but that's the idea. You see which queries your application will need at different steps. So these are tasks or application steps. And you see which queries they need to be able to function. And then you also know, well, to execute queries here, you will have information retrieved from query one. So you have this flow dependency. So once you have these all networks here, and then you need to select all sensors for a network, you know that you will be getting specific network name or ID from the previous task. So again, you can put it in words, or you can put it in a diagram, and that's something that you can, the diagram is going to be much more precise and easier to read. So logical data model, given those two models, application and data, the conceptual data model, then there are some rules you can use to map. So if you look at the conceptual data models, the conceptual data model, there are two rules that are related that you can use to derive tables from that. These are now tables in Cassandra. And for application, there are three rules. So the first mapping rule says that entity and relationship types map to tables. That's very, very simple. That's what, and of course the attributes of entity and relationship types will map to columns, right? But how do they map? If you, in your query, you have a quality search attribute, so you say, in my query, I want to retrieve sensors for a given network. So network is a quality search, right? Network has to be equal to something. That network attribute is going to map to beginning columns of the primary key. It will form partition key completely, or maybe there will be, if you have many of those equality search attributes, you can have a choice. So all of them become partition key, some of them become partition key. Inequality search attributes will become clustering column, because inequality is the only supported on clustering columns, and ordering attributes will also become clustering columns. They only supported on the ordering is only supported on clustering columns. Finally, and this rule is frequently forgot, and I said told in the beginning that keys are super important and cardinalities are super important. So once you design based on the query, everything, you still need to remember from your conceptual data model, will this still give me unique entities or relationships? So you need to make sure that the keys you identified on the conceptual data model will be preserved in your primary key design. Okay, so let's see how it works on one simple example. So I have this conceptual data model you've seen before, and the query: find raw measurements for a given location and a date time range, order by timestamp. Okay, so I will be finding measurements. This is the temperatures, right? A given location. So location is here. This is sensor. So I need to cover all of these, right? And the location is equality. Date time range. So it's inequality. So this timestamp is going to become a clustering column, as you may already know. So the first mapping rule, I'm going to query temperatures based on the sensor location. So this is what I'm going to have. I'm going to add latitude, longitude, timestamp, value. So attributes from all of these, basically, from both entity types. The second rule, equality. So I'm going to have location fixed to some value. So these two will become partition key, right? So these two will be first. They will form the beginning of primary key. In our case, it makes sense to make them both partition key, denoted as K. And then the next rule, and I'm going to have inequality on my timestamp. So timestamp becomes clustering column. And right now, it's by default ordered in ascending order. And then I'm going to order by timestamp. This is rule 4. And ordering by timestamp, it has to be clustering column. It's already clustering column, but I need to descend in order, so I will change the ordering to descending order. Final step, what makes do it? So many people, I've seen common error. People start here and they forget that to check whether this is enough to form the primary key that will also preserve uniqueness of that relationship. Essentially, this is a relationship words, right? We retrieving temperatures recorded by sensor at specific location. Temperatures recorded by sensor at location. So that very traversing, the key is sensor ID plus timestamp. That's what uniquely going to identify this one particular measurement. So I still need to add, according to rule 5, I still need to add sensor to preserve that uniqueness. That's how I design table. This is not the simplest table, but it's a good illustration what it may take. And then you do it for all the tables, and you get logical data model that looks like this. This is called logical data model, or represented by Chebotko diagram. We have actual tables with partition key, clustering key defined, ordering as needed, and we still have those access patterns that we can later express in CQL. The next step is to optimize. There are many important optimizations that you may apply, such as partition size, whether you use batches or not, indexes. Sometimes it makes sense to use indexes. Sometimes, in most cases, it does not. Materialized views, they are great, but there are some problems with them as well. What to do with concurrent data access? Timestamps is a separate topic, separate treatment, because they are handled a little bit differently in Cassandra than in other databases. Okay, and then once you apply those optimizations, you will be able to design the physical level Chebotko diagram or physical data model. So what changed here? We did add data types, right? We did add data types, but we also, in green, we show some columns that were changed, introduced. So what happened here? What happened here? So the first query wants us to retrieve all the networks. So we want to retrieve all of them from a single partition. So which partition is that? We basically introduced a bucket, dummy column with value all, for example, and there will be only one partition. And then we nested all the networks in that partition, assuming we don't have millions of networks. We're going to have dozens maybe in this application. So dozens of rows nested in one partition. Before, what we had before is we simply had name as a partition key. So which means if we want all of them, we will have to select all from the table, potentially ask every node to give us data. Now we only ask one node or a set of replica nodes to give us just one single partition. Very efficient. And for the temperatures by sensor, for this table, we did as well, we did bucketing. So because there will be, so to get all the temperatures across all sensors for a network, the partitions can be very big, can become very big. So we introduced weak as a partition key, and this allows us to limit the size of the partition and retrieve it more efficiently. And we also the query too we did not discuss, but it is based on the date hour. So we also may introduce this column instead of timestamp, I believe. Anyway, at that point, once you optimize your schema, you know that it's going to perform efficiently, it's correct, it's efficient. So logical data model was about correctness, physical data model about efficiency. Now you can define your tables in CQL, and I'm not gonna spend much time here because you will have the next lab, you will actually create those tables in Astra DB. So another way to look at this data modeling methodology versus relational data modeling methodology. So relational databases have one too. It's well defined as well. So it also has conceptual data model, which is independent of database actually. The same conceptual data model can be used in both relational and NoSQL. There are rules to map it to relations. Then there is normalization C that maps that or decomposes those relations into smaller relations with specific normal forms. And then physical optimization concerns efficiency. This is where queries are involved. Okay, at this step of physical optimization, the big difference for Cassandra data modeling methodology is that queries will be here in the very beginning along with conceptual data model. So it's in a way it's different. It's important to understand this major difference, but in a way it's actually simpler. There is no normalization theory. You don't worry about that. You worry about supporting queries. And for relational databases, even after you normalize, you do a lot of work to normalize it, then you realize some queries are not doing very well. So you will have to either create some additional indexes or maybe denormalize. So you will undo your normalization to make those queries more efficient. Okay. And before we do the next lab, there is also a demo, a quick demo that uses KDM data modeling tool. So it's kdm.cachly.com. Again, you can find the information on GitHub. So this is the demo. You don't have to do it. You can just watch. But if you want to repeat it, you are able to repeat it. So in my case, so how it works, I can define conceptual data model if I want to, and I can specify queries. I can generate tables automatically. So we have something well-defined, automated, right? User, movie, user watches movie, and then you should be able to connect them. So user can watch many movies, and a movie can be watched by many users as well. Okay, we can have some attributes. Oops. Something simple. So user ID, and so I definitely need, the first thing I did cardinalities, entities, relationship, cardinalities. Now I need to make sure I have all the IDs, and movie will be title and year. Title and year. Okay, and I will designate them as keys. And there are many features here. I'm going to just show some simple. So this is very simple data model. Let me add some non-key attribute, user name. So, and the query I want to ask is find me names of users who watched a specific movie. Okay, so think about table that you need to create. Names of users who watched a specific movie. Okay, and I'm not even trying to create the table yet. I want to define the query itself. So second step, access pattern. I will say this is what I'm looking for. Find name of the user, and this is what I have. I have the title of the movie and year of the movie. And of course, there are many more things, ordering and everything else. So it can be more complex, but I'm going to generate logical data model for this one query. And these are choices. These are 4 tables I can select. Now you can think about which one is the best given title year, or year title. So this doesn't matter which one. I probably like this one, title year, better, just for human readability. You can also do clustering columns, and I don't care about them. This one is more efficient for me, because given one specific movie, I want to retrieve one partition for names of the users who watch that. But you can see the ID was added there automatically and all of that. So let's then generate the physical one. Change the name if you like. Change the data types if you like. The year, for example, will be int. The ID may be ID. Okay. And generate SQL. So this is the table definition. Right? This is a table definition. So this is how it's done, and you can load the data model that that we already defined for the sensor data. Yeah. So it's the link is on the website.
Yeah, that is really cool. I can see how that would totally be useful in just up in generating tables optimized for a specific query like that, and just getting the CQL. That's awesome.
Yeah, and especially in the beginning, you can if you only learning how to do it, it's not easy to just it's easy to make mistakes, not specifically the uniqueness. I've seen, I mean, this is common for people who have experience working with Cassandra. May not be that may not be that easy to model data.
Oh, right. Yeah, that is definitely the hardest part of kind of putting this all together. That's for sure.
Yeah, so this predefined project is what you've seen already, right? And it has all those queries, 4 queries, and you can generate logical data model, select what you need, generate physical data model, generate SQL. So with a few clicks, right? So what was the most difficult part? The most difficult part was this one, right? And the second, the most difficult was defining your queries correctly. Everything else was done for you. So it's if you even if you design in yourself, if you're not sure, this is a tool you can verify that your design whether it's right or not. Okay. So and with that we have one more lab.
Yep.
One more lab, and this is the lab 3, sensor data modeling. So let's go to this section 9 of the README file. Start Git pod. Again, we will need the token, but this time we are going to use the sensor data key space. So you will actually create those tables that we just talked about how to design them. You will create them and you will query them, and then you will see how those queries actually work, why they're efficient, and all of that. Okay. So let's, well, it didn't want to start. Let me see. Well, we do have known problem. Let me stop it. That it, in rare cases, I don't know what's the percentage, it may not, the layout may not do the correct thing because of the it's hard to get the timing there within the Git pod.
Yeah. Sometimes that can be tricky.
Difference. Yeah. That's the second time. It started, but the layout was not right.
Right.
Okay, this time it worked.
Yeah, I was going to say, that's looking better already.
Yeah. So let me get my token. Okay, so start with Astra DB. Again, same thing. Set up CLI and provide your token. Okay, connected. Let's list the databases. We have 2 of them. Nothing changed. Okay. Oh. Token provided is invalid. Did I copy the wrong token, or was it? Just give me a second. Sometimes even an extra space could be a problem.
Yep. Just a reminder, folks, this is live.
Yeah. Yes.
There we go. Oh. Yeah, much better.
Yeah, so maybe first time I copied my token was maybe extra space, and it didn't work. So we creating the sensor data key space, unless we already have it, and we already have it, so it should say that it already the database exists, the key space already exists, so we are ready to use it. Let's start the CQLSH and go to the next step. So this is our table network, table temperatures by network, sensor by network, and so on. I will just create all of them. You've seen tables before. Four tables, I can.
Uh-oh.
Operation timed out, okay.
Yeah, sometimes that happens on schema operations.
Yeah. I did click multiple times or something. So let me describe tables. I have 4 tables I wanted to create. I created
Excellent.
them. And I'm going to insert data using this CQL script, which is a bunch of insert statements into those tables. Now I can check, what do I have? I have 2 networks in the networks table. So they are called the forest net and volcano net. And I have these rows in my temperatures by network. So these are hourly aggregates, average temperature for each hour. I do have more data. So these are all my sensors. There are three sensors in ForestNet, 2 sensors in VolcanoNet, and these are the raw measurements for those sensors. Okay, and then you can go through the design of each of those queries that we talked about. So how do you retrieve all your networks from one partition? Remember, we have this bucket with value all. We accessing just a single partition and retrieving both of them. In the next one, we need to find hourly average temperatures for every sensor in network ForestNet and given date range within, and that date range is within specific week. So, and there is ordering involved. So this one is more complex. We have network, we have specific week. This is part of the partition key, and we have date and hours. So that's what we will do. Okay. So range on data and hours. This second one is a little bit more complex because the date range covers 2 weeks. 2 weeks. So I will look at solution 2. So what you can do is you can specify in, and you specify 2 weeks. And in this case, accessing 2 partitions. Less efficient than 1 partition, but that's what we have to do because we split the partition based on week. Done. So an easy one, get all the sensors in the network. That should be super easy to understand. And the last one is getting measurements for particular sensor on a particular date and ordering by timestamp. So sensor equals something. Again, the reason we are able to execute these queries is because we designed our tables specifically for these queries. And of course, we understood the data to be able to do that. And we are at the end of this section. So the next section is going to be about optimization. So we are able to design the correct schema, but we will also need to optimize that schema for performance. So just a quick a summary of what you learned today. So this is the most important part. We finished it, and we will still, I think we will have time to talk about indexes briefly, and then we'll wrap up. So the key takeaways for data modeling principles: know your data, know your queries, nest data, duplicate data. We talked about that. Most efficient access pattern is when you access one partition. Your query only touches one partition, or maybe a few partitions if you had to split partition, maybe a few partitions. Okay, so that's important. And then the primary key defines uniqueness, defines distribution, and defines how you can query that, queryability. So you need to remember that. And the methodology we talked about, it may be new to you and seem challenging and complex, but it's actually not more complex if you than relational data modeling. So if you had training, if you took data course, undergraduate database course in the university on relation basis, and you did the normalization series, you know that that one is more, the relational database data modeling is more complex because it's integration database. Yep. And you are talking here, we're just focusing on one application much simpler. And KDM, we used KDM. This is the tool that is available for you for free that you can play with. And for the optimization techniques, Aaron, do you want to talk about indexes?
Yeah,
this is one.
I know we have a few sections under optimization techniques, but I think I'll just jump right to the indexing and materialized views section. Just it looks like we got 3 minutes here to go, but we'll kind of still try to provide some value at least on indexing itself here. So the idea with indexing and oh, sorry, what? Oh, yeah, I could go in slideshow mode, shouldn't I? All right. So the idea with data or indexing in a distributed database is that there are really kind of two approaches you can take. You can actually create a table to function as an index, so like a lookup table. And these are what's known as like distributed indexes, and their advantage is that they're highly scalable. So you'll actually still be able to like solve queries in a minimum amount of hops through the cluster. Local indexes, on the other hand, are technically not. We have some additional options, for building out secondary indexes in Cassandra. You just have your typical secondary indexes. We also have SS table attached secondary indexes, as well as storage attached secondary indexes as well. See, the main thing though to understand is really kind of how these indexes or secondary indexes work. So the thing is that when I'm querying on a column that has a secondary index, there's no hash that's happening on that column, which means that that Cassandra doesn't know, right, at least at the onset of the query, when we start figuring out the pattern, the access pattern, is that it doesn't know which node has the data it's looking for. So it kind of has to go to each one of these nodes and check the index on the table to see whether or not it has that data. So that node you're going to kind of takes on that role of coordinator and of looking at the rest of the cluster. So if you remember before, when Artem talked about some operations are better on smaller clusters versus larger, the larger your cluster gets, the slower those secondary indexes are going to perform, just because of those lookups that they're going to have to make. So that's really what kind of happens when you do a query with Cassandra or Astra that's not optimized as well as it should be. For storage attached indexes, it really is the best available. You get your faster writes. They take up less space on disk. You can actually use multiple indexes in one query, so that is kind of an advantage on convenience there as well. But your reads can be a little on the expensive side. Similar limitations to what we just mentioned with secondary indexes. And of course, again, it's more about convenience rather than performance. But you actually can create it. The CQL is available there on screen. You can see you just have to kind of mention that storage attached index class when you create it, and it should take care of that for you. Now, as far as like when to use a secondary index, it really is like use case dependent. If you're looking at like a real-time transactional query, you're bringing in rows from like a large multi-partition or multi-row partition. So you already have your primary key defined, and you're really just adding that index in there as a way to like quickly find something inside a partition. That's actually a really good use case. But when you're looking at like the expensive analytical query, you're pulling back a large number of rows, you're reading multiple partitions. And again, multiple partitions means you're reading from multiple nodes, and that's not going to be efficient. And maybe you've indexed like a low cardinality column. There's going to be a lot of values, a lot of rows that it has to check, that it has to verify. And then it has to bring all of that data back to that one coordinator node that has to manage it on its putting that result set together and then sending that back to the application. So that can get that can be a little tough, but when you're using something like a middle of the road cardinality, it's not terrible. I guess is what we're saying here in terms of how to do an analytical query. If you have a small cluster, we've mentioned this a couple of times, like 3 to 10 nodes with RF3, using an index, that's not too bad. When you're talking like 30 to 100 nodes, yeah, that's going to take some time to go ahead and pull each one of those. I kind of mentioned before about using an index in one of the questions I was asked in the chat. Like if it's a one-off corner case, if it's something that's not going to be run often, hey, that's a good use case for it. It's something that yeah, maybe you do it like once a day, once every other day or whatever. You don't really want to build a table for it. Yeah, a secondary index query isn't so bad. And also using it with limit is a good idea too. Especially of one that can potentially bring back a lot of rows. Cutting that off at like 5 or 10 rows or whatever is certainly a better option than letting it run through and pull 1,000 rows back. And to just remember too that it's convenience over performance. It's weighing out how much work do you want to do to create a new table and keep that table in sync, kind of with the rest of them, versus how much performance is that worth to you. So that's like I said, it's really use case dependent. It's about kind of evaluating what your what your current needs are and going from there. Oh, sure. How can we look at the execution plan for a CQL query, whether it's using a sequential scan or an index scan? Well, one thing you can do inside of CQL shell is to actually you can actually turn on tracing inside of CQL shell. And what'll happen is you'll get back like kind of a step-by-step breakdown of each individual part of the query that it has to put together. And you'll even see the IP addresses of the other nodes that it has to interact with and work with. So you can really kind of trace that. Literally, you can kind of trace its steps through the cluster while it puts that result set together and brings it back to you. So that's actually a very good question there. Artem, I think that's the last. Yeah, and then we go to materialized views. I think we're out of time for that, so we probably want to skip to the end, huh?
Yes, sure.
Oh, do you want to take over?
So
yeah, okay.
Yeah. So what's next? Of course, next week we have the third workshop, and that one will be specifically to design the application, to write code. I believe there will be Java and Python and JavaScript. So you will be able to access. So now you created this sensor data database, loaded some data. Now you will be able to access it from your application. Of course, to continue learning about data modeling, you can do the homework. So the GitHub repo, the README contains instructions how to submit that homework and get the badge if you incline to do so. But also we have, so the example of sensor data modeling came from this data modeling by example learning series. And there are 6 more examples, and those examples are actually more, some of them are more advanced, so you can learn even more, and including some of them use indexes, some of them use materialized views, some use batches, and you can learn about those features as well. For homework, we do ask you to do the time series data modeling. Again, it's the instructions for the homework. Finally, if you want to learn even more, you can read a couple of blog posts that can get you started on, can improve your understanding of data modeling, and including the how to design data model for IoT. And there is a specific problem there, and 5 different models are discussed, their advantages and disadvantages. So that's a useful exercise to understand reasoning. Again, there are materialized views, there are indexes used there, and so on. Stay in touch. We have Discord where you can ask questions. We have Academy with video courses. We have workshops, that one of them you're in right now. And we have YouTube channel with all kinds of topics covered there in our video materials. It's not only workshops, there are many other demos, how-tos and tutorials that you can find there. And with that, we complete this workshop, and we thank you for staying with us till the end, and hope it was useful, and hope you will come next week as well.
Thank you very much, everyone. Have a good day.
Thank you.
And as always, don't forget to click that subscribe button and ring that bell to get notifications for all of our future upcoming.
Imagine a being gifted with powers from the goddess of Cassandra, who grew those powers until she could multiply at will, move with limitless speed, and unmask hidden knowledge. With those powers, she was able to fully understand the connectedness of the world. What she saw was a world in need of understanding. From that day forward, she sought to bestow her powers on all who came into contact with her, empowering them to achieve wondrous feats.